Okay, let's break down this problem about finding the number of microstates for distinguishable particles. So here's the problem we are looking at. We have 4 particles and they are distinguishable, meaning we can tell them apart. These particles can occupy 3 different energy levels, 0 epsilon and 2 epsilon. We want to find out how many different ways these 4 particles can be arranged among these energy levels, such that their total energy adds up to exactly 4 epsilon. Then we'll see which of the options, 20, 24, 11 or 19 is the correct number of microstates. Alright, let's set up the problem. We are given the number of distinguishable particles, which is n equals 4. The available energy levels are E0, which is 0 E1, which is epsilon, and E2, which is 2 epsilon. And our target total energy is E total, which is 4 epsilon. Now, how do we think about this? We can describe any arrangement by saying how many particles are in each energy level. Let's use n sub I to represent the number of particles occupying energy level, E sub I. So n0 is the number of particles at energy, 0 n1 is the number of particles at energy epsilon, and n2 is the number of particles at energy 2 epsilon. A specific way of distributing the particles is called a configuration defined by the set of numbers n0, n1 and n2. Because these particles are distinguishable, the number of microstates, which we denote by W for a given configuration, n0, n1, n2 is calculated using the multinomial coefficient formula. It's W equals n factorial divided by n0 factorial times n1 factorial times n2 factorial. And of course, the total number of particles n must be the sum of the particles in each level, so n equals n0 plus n1 plus n2. Now, any valid configuration must satisfy two main conditions, which are like constraints on our n0, n1 and n2 values. First, we have the conservation of particles. The total number of particles must be 4, so n0 plus n1 plus n2 must equal 4. Second, we have the conservation of energy. The sum of the energies of all particles must equal 4 epsilon. So n0 times 0 plus n1 times epsilon plus n2 times 2 epsilon must equal 4 epsilon. Assuming epsilon is not 0, we can divide through by epsilon, and this simplifies nicely to n1 plus 2. n2 must equal 4. So what we need to do now is find all possible combinations of non-negative integers for n0, n1 and n2 that satisfy both of these equations simultaneously. Equation 1 n0 plus n1 plus n2 equals 4. And equation 2 n1 plus 2 n2 equals 4. We can start by looking at the second equation because it only involves n1 and n2. We can rearrange it to solve for n1 n1 equals 4 minus 2 n2. Since the number of particles n1 must be greater than or equal to 0, this means 4 minus 2 n2 must be greater than or equal to 0, which implies 2 n2 must be less than or equal to 4, or n2 must be less than or equal to 2. Since n2 must also be a non-negative integer, you can't have a negative or fractional number of particles. The only possible values for n2 are 0, 1 or 2. We'll examine each of these cases. Let's take case 1 where n2 equals 0. From the energy equation, n1 plus 2 times 0 equals 4, which gives us n1 equals 4. Now we use the particle conservation equation n0 plus n1 plus n2 equals 4. Substituting our values, n0 plus 4 plus 0 equals 4, which means n0 must be 0. So our first valid configuration is n0, n1, n2, which is 0, 4, 0. Now let's calculate the number of microstates for this configuration, which we call W1. Using our formula, W1 equals 4 factorial divided by 0 factorial times 4 factorial times 0 factorial. 4 factorial is 24. 0 factorial is 1. So this is 24 divided by 1 times 24 times 1, which simplifies to just 1. Okay, moving on to case 2 where n2 equals 1. From the energy equation, n1 plus 2 times 1 equals 4. So n1 plus 2 equals 4, which means n1 equals 2. Now using the particle conservation equation, n0 plus n1 plus n2 equals 4. Substituting n0 plus 2 plus 1 equals 4. So n0 plus 3 equals 4, meaning n0 must be 1. Our second valid configuration is n0, n1, n2, which is 1 to 1. Let's calculate the microstates for this configuration, W2. W2 equals 4 factorial divided by 1 factorial times 2 factorial times 1 factorial. That's 24 divided by 1 times 2 times 1, which is 24 divided by 2. So W2 equals 12. Finally, let's consider case 3, where n2 equals 2. From the energy equation, n1 plus 2 times 2 equals 4. So n1 plus 4 equals 4, meaning n1 must be 0. Using the particle conservation equation, n0 plus n1 plus n2 equals 4. Substituting n0 plus 0 plus 2 equals 4. So n0 plus 2 equals 4. meaning N0 must be 2. Our third valid configuration is N0, N1, N2, which is 202. Let's calculate the microstates for this configuration, W3. W3 equals 4 factorial divided by 2 factorial times 0 factorial times 2 factorial. That's 24 divided by 2 times 1 times 2, which is 24 divided by 4. So W3 equals 6. So to summarize, we found 3 distinct configurations that satisfy both the particle number and total energy constraints. Configuration 1, with particles distributed as 0400, satisfies the total energy of 4 epsilon and has 1 microstate. Configuration 2, with a distribution of 1 to 1, 1, also meets the 4 epsilon total energy requirement and corresponds to 12 microstates. Finally, configuration 3, showing 202 particles, also has a total energy of 4 epsilon and corresponds to 6 microstates. To find the total number of available microstates for the total energy of 4 epsilon, we just need to add up the number of microstates from each of these valid configurations. Total microstates equals W1 plus W2 plus W3. That's 1 plus 12 plus 6. Adding those up, we get a total of 19 microstates. So there are a total of 19 available microstates for our system of 4 distinguishable particles to have a total energy of 4 epsilon. Looking back at our options, the correct answer is 19, which is option number 4.